Welcome to the podcast of machine learning.
Hi there. So today we're diving into something pretty critical in generative AI. You know those amazing images, the videos generated by models like Mask-GIT?
Oh yeah, incredible stuff.
Yeah,
Visually stunning.
totally. But there's a hidden cost, a big one. They are often cripplingly slow to actually generate stuff, at inference time. And they eat up tons of compute power. It's almost like a little energy crisis brewing.
Right, and it's not just about the models being massive, is it? It's more subtle than that. It's about how they work iteratively.
Exactly. It's about redundancy. The main issue is that these algorithms, they refine the output over multiple steps, multiple passes through a transformer model.
Okay.
But here's the thing. The model capacity, like the sheer size and power of the model, it stays exactly the same for every single one of those refinement steps.
I see. So even when it's doing the relatively easy stuff at the beginning.
Precisely. Imagine you're refining a blurry photo. Step one might just be figuring out, okay, that's the sky, that's the ground. Pretty coarse stuff.
Right.
But current methods use the same heavyweight champion model for that. And for the final tiny details in step 10, it's just wasted effort. Uniform capacity repeated over and over. That's the bottleneck.
Okay, so massive computational waste. And that's the problem that this approach we're looking at today, magnets, is designed to tackle.
Exactly. Masked, generative nested transformers with decode timescaling. It's a mouthful.
Yeah, let's stick with magnets.
Good call. So the mission here is to see how magnets gets you similar, high-quality results, but with potentially like up to 3 times less compute.
3 times less. That's significant. How does it pull that off?
It really boils down to 2 key ideas, 2 main strategies.
Okay.
First, they design a smart schedule for scaling the model size during decoding. The insight is not all parts of the generation process need the same amount of computational muscle, right?
Makes sense. Allocate resources dynamically.
Yep. And second, they use caching, specifically key-value caching, or KV caching, to store and reuse intermediate calculations. Stop recomputing things you already figured out.
Smart memory. Okay, let's dig into that. Maybe start with the baseline. You mentioned Mask-GIT as kind of the state-of-the-art for this parallel generation.
Yeah, Mask-GIT and similar models are already a big leap from older methods that generated things 1 pixel or 1 token at a time. They do parallel decoding, generate lots of stuff at once, and then refine it.
But you said it still has this redundancy problem. Where's the waste in Mask-GT specifically?
It's that constant model capacity thing we talked about. Mask-GIT generates tokens in parallel, masks some, refines them, masks others, refines again. Multiple passes.
Right.
But the transformer doing the refining, it's the same size, same complexity every single time. So early on, when it's just figuring out the broad strokes, the big shapes, using the full giant model is serious overkill. Overcomputing.
Gotcha. So that directly leads to the core idea, the hypothesis behind magnets.
Yeah.
We need dynamic scaling.
Exactly. The logic is pretty straightforward when you think about it. Initial steps. You just need to get the rough layout, the coarse global structure. That's relatively easier. A smaller, less powerful model should be fine.
Right.
Later steps, now you're filling in the fine details, the complex textures. That's much harder. That's when you need the full power, the larger model.
So match the compute power to the difficulty of the current task.
Precisely.
Yeah.
And it's not just a theory. They actually found some really cool empirical evidence for this.
Oh, yeah. What do they see?
They looked at what the model was actually generating at each step, and they found this pattern. Generation usually starts by unmasking tokens in the background areas, the simpler, larger patches of color.
Like the sky or a wall.
Exactly. And only in the later iterations does the model's focus shift to the main object, the foreground, where all the complex details usually are.
That's a great visual. So the model itself shows this progression from coarse to fine. It kind of justifies spending less compute early on.
It really does. It's like, why use your most expensive fine-tipped brush to paint the entire background wash? It doesn't make sense. If the complexity changes over time, the compute budget should too.
Okay, so the why is clear. Now the how. How do you actually implement this variable model size without just loading different models, which would kill your memory budget?
Right. That's where the nested part of magnets comes in. They use nested models, building on an approach called Matformer.
Nested models. Tell me about that structure. How does that work?
It's pretty clever architecturally. You basically train a set of models of different sizes, say small, medium, large. Let's call them M1, M2, and the full model M.
Okay.
But the crucial part is that M1's parameters are literally a subset of M2's parameters, and M2's are a subset of M's. They share the underlying weights.
So they're not separate independent models.
No, exactly. The smaller ones are like submodules within the larger one. This means you get the ability to run different effective model sizes, but the total number of parameters you need to store in memory is just the parameters of the single largest model, M.
That is the variable capacity without the memory explosion. Okay, so they have the structure. Now, the strategy, the scaling schedule. You said magnet scales up.
Yes, they gradually increase the model size over the decoding iterations. Start small, then medium, then maybe finish with the large full model.
Okay, but I'm still stuck on why scaling up is better for speed.
Hmm.
Wouldn't you want to scale down? Use the big model first for the hard stuff, then the small, fast model for the final quick touch-ups.
Yeah, it seems counterintuitive, doesn't it? And they definitely tested different schedules, but scaling up turned out to be the winner.
Why, though?
It comes down to how many tokens you're processing at each stage in parallel decoding. In the initial steps, you have the most masked tokens, right? A huge chunk of the image needs generating.
Right, lots of work to do.
So using a small, computationally cheap model to process that high volume of tokens early on is actually very efficient. Get the bulk done quickly and cheaply.
Okay.
Then, as you proceed, more tokens get unmasked, finalized. The number of remaining masked tokens drops significantly in the later steps.
So fewer tokens to process later on.
Exactly. And that's when you bring in the larger, more powerful, but more expensive model. It can focus its heavy-duty capacity on those few remaining, but probably trickier tokens that need fine detail.
You get it now. It's about matching the model cost to the volume of work at each stage, not just the conceptual difficulty. Handle the bulk cheaply, then use precision power for the refinement.
You got it. So that's the dynamic model size part. Now, the second pillar, reusing information with caching.
Yeah.
How does KV caching fit into this parallel world?
Right, the key value caching.
So in these parallel decoders like masked GIT or magnets, once a token is generated and unmasked, it's basically considered done. It's not going to change in later refinement steps.
Okay, it's locked in.
Locked in. So the moment it's unmasked, the model calculates the key and value vectors for that token. These are using the attention mechanism, right? Magnets caches these KV pairs for all the unmasked tokens.
And the benefit?
Huge computational savings. In the next iteration, when the model is calculating attention again, it doesn't need to recompute the keys and values for all those already finalized unmasked tokens. It just fetches them from the cache.
So attention only needs to be fully computed for the remaining masked tokens interacting with the cached ones.
Essentially, yes. It drastically cuts down on the redundant calculations within the attention layers step after step.
Okay, that sounds like a powerful combo. Smaller models processing the bulk early on, plus caching the results for finalized tokens. The big model later only has to focus its power on the few remaining tricky bits, using cached info for context.
That's the core efficiency loop. But there's always a but, isn't there?
Usually. What's the catch with caching here?
Well, this aggressive caching can sometimes slightly hurt the final quality. Two reasons, mainly.
Okay.
First, because the unmasked tokens are totally frozen, they don't get updated based on things generated later. Second, and this is specific to the nested models, when you switch from, say, the small model to the medium model, the dimensions, the size of the query vectors, might change slightly because you're using a different part of the nested structure. This can create a small mismatch with the KV pairs cached from the previous smaller model.
So the cached values might not perfectly align with what the new, bigger model expects, leading to a little bit of quality degradation.
Exactly. It's often a small drop, but noticeable if you're aiming for top-tier quality, a classic speed versus quality trade-off.
So how did magnets get around that? Did they just accept the small quality hit for the speed?
Nope, they came up with a pretty elegant fix. They call it intermittent cache refresh.
Cache refresh. Sounds like clearing your browser cache.
Kind of. The idea is simple. They strategically discard the cache and force the model to recompute all the KV pairs from scratch at specific points.
When? When do they do this refresh?
Precisely when they switch model sizes in the nested schedule. So when going from the small model to the medium or medium to large, they just flush the cache for that one step.
So you pay a one-time cost of recomputation right at the transition point.
Exactly. But that recomputation ensures that the KV pairs are perfectly aligned with the new, larger model dimensions that are about to be used. It essentially recalibrates the system.
And that bridges the quality gap caused by the caching.
That's what they found, yes. This cache refresh step brings the quality right back up, basically eliminating the downside of caching while keeping most of the speed benefits.
Clever. Okay, so we have this sophisticated system. Nested models, scaling schedule going up, caching, and strategic cache refresh. How on earth do you train something like this efficiently, especially the nested part?
Yeah, training is key. They use something called progressive online distillation.
Distillation, like a smaller student model learning from a bigger teacher model.
Exactly. But here, it's happening within the nested structure during a single training run. The loss function isn't just about matching the ground truth image.
What else is in there?
It also includes a distillation loss. The goal is to make the smaller nested models mimic the outputs or internal representations of the next larger model in the hierarchy.
So model M1 learns from model M2, and M2 learns from the full model M.
Precisely. The smaller model, my, uses the next bigger one, my plus one, as its teacher. This keeps the smaller models aligned with the capabilities of the larger ones.
And how do they balance learning the ground truth versus learning from the teacher?
They use a weighting scheme on the loss. Initially, the training focuses more on the ground truth loss getting the image right.
Makes sense.
But as training progresses, the weight for that ground truth loss is linearly decreased, eventually going down to 0. At the same time, the weight for the distillation loss increases.
So later in training, it's mostly about ensuring the smaller models behave like the bigger ones.
Exactly. It helps prevent the smaller models from diverging too much and ensures they benefit from the knowledge implicitly learned by the larger capacity models during training.
And does this nested training with distillation actually work better than just training separate models?
Get this, yes. The paper shows that training these models using this nested progressive distillation approach actually produces better performing models, especially the smaller submodels, than if you just trained independent standalone models of those exact same sizes from scratch.
Wow, so the nested structure and the distillation act like a really effective regularizer or knowledge-sharing mechanism.
It seems so. It's like the smaller models get a boost from being trained jointly with and guided by the larger ones. We see this particularly in the video generation results they reported.
Okay, speaking of results, let's talk numbers. This sounds great in theory, but what's the actual payoff? The compute savings for image generation.
Right, the bottom line. On a standard benchmark like ImageNet, generating 256 by 256 images, they compared magnets to strong baselines like Mask GIT++ Sun.
Yeah.
Magnets achieve quality that was pretty competitive. For example, an FID score of 2.9 for magnets versus maybe 2.3 for the baseline FID is better, so it's a bit worse, but still very strong quality.
Okay, competitive quality.
Okay.
And the compute.
That's where it shines. It used about 2.65 to 3 times less compute, measured in GFLOPs, gigafloating point operations, to generate each image.
2.5 to 3 times reduction in computation for a reasonably small trade-off in FID. That's huge for practical deployment.
Absolutely. That kind of efficiency gain makes a real difference.
And you mentioned video. This isn't just for static images, right?
Not at all. The core principles is dynamic scaling, caching. They apply to any kind of iterative, multi-step generation process using transformers.
So it worked for video, too.
Yep, they tested it on datasets like UCF-101 for generating video based on a class label, and Kinetic 600 for predicting future frames in a video.
And the compute gains held up.
They did. In some video scenarios, the compute reduction was even larger, sometimes up to 3.7 times faster than the baseline.
Okay, so summarizing the efficiency win. It's really this combination, isn't it? Nested models for memory efficiency, scaling up the size to match the workload volume, and then the smart caching with the refresh trick to maintain quality.
That seems to be the winning formula they found. It's a move away from just throwing constant brute force compute at the problem towards a more intelligent, adaptive allocation of resources over time.
Which brings us to why this matters to you, listening out there. This isn't just an academic curiosity, right? This translates directly into real-world benefits.
Oh, absolutely. Faster inference time, better real-time efficiency. That's the payoff.
Could you give us a concrete example? Like, what does this mean for latency, the time you actually wait?
Yeah, they had a great table on this. For their large Excel-sized models, the standard baseline might take around 712 milliseconds to generate an image. That's, noticeable lag.
Almost a second, yeah.
With magnets, using the scaling and caching, that latency dropped to 285 milliseconds.
Wow, from over 0.7 seconds down to under